Welcome to third lecture of course on corrosion, environmental degradation and surface engineering. In this lecture, we will be discussing on wear mechanisms. We have already understood wear related material surface degradation can lead to the failure of top layer. Over the time, this process will weaken the material and cause a product failure. So, we need to take care appropriately. We say wear will happen when the two surfaces rub against each other and are subjected to mechanical load. This causes surface to lose material and in worst case it will break or product will break. In our earlier lecture, we have discussed about a few mechanisms related to we have highlighted a few mechanisms related to mechanical wear. We mentioned about the adhesive wear, abrasive wear, fatigue wear, erosive wear, fretting wear, melting and diffusive wear. We named this kind of wears, but we need to explain in much detail. So, in the present lecture, we will be highlighting or we will be discussing adhesive wear. In extreme form, adhesive wear between the two metals can form a cold junction and bind the two surfaces together and completely stop the relative motion, a seizure or we can the failure of the system. So, there is a need to understand the wear mechanism. Let us start with adhesive wear. We say this is very common in metals. That means, it is more dominantly used in the metals. Naturally, what is the reason? In our earlier lecture, we discussed that all the contacts will occur only at the asperity levels. Like the asperity level over here, and because this asperity contact are much smaller than the apparent area. That means, the real area of contact is a 1 to 2% or maybe 5%, sometimes even lesser than compared to the apparent area. What will happen because of that? There will be extreme stresses. And another one, when this metal comes under plastic deformation and very close to each other, we say when the separation is a lesser than 1 atomic diameter, what will happen in this situation? Metal will allow electron transmission. That means, a green color metal can transmit the electron from green color in this metal to the blue color metal, or blue color metal can transfer the electron to the green color metal. What will be the problem in this situation? There will be interchange of electron transmission or there will be transmission of electron, and because of that there is a possibility of micro weld. This micro weld, if we apply force or tangential force to move relatively the green metal against the blue metal, what will happen? There is a possibility that a chunk of the blue color metal, which is a softer in nature compared to the green one, material will get transferred to this, and this is a beginning of wear process, or this is a adhesive wear or beginning of the process which will lead to the fatal wear. So, this is important to understand. Another important thing is that if the metals are the clean, sometimes we use a word that we should use a clean metals. There will be more and more problem if we are going to think about the clean metals. That means, a material is manufactured and immediately we are going to place it for the usage. What is the problem? Reason being the very clean metal, then possibility of the transmission of electronic will be instantaneous, spontaneous, and this will be completely independent of temperature. That is why we say that this micro welds are related to the cold weld. The cold welding happens. We can name this complete phenomena as a stronger junction. Why do we say it is a stronger junction? Because when we are trying to move one metal against another metal, the shearing does not take place so easily, and what will happen? It will not be able to move easily and there will be extreme wear, and this is what we mentioned, that shearing is not easy and that there is a stronger junction. So, what we need to do? We need to make some sort of weaker interface. Our interface shear strength or shear stress which is induced there needs to be weaker. How it is possible? Let us take this is a metal 1, this is a metal 2, and they have asperities, maybe some sort of the plastic deformation we are able to see. That means, there is a need to move the relatively metal 1 compared to the relative to the 2 there is a possibility there will be a junction here, but this is a weaker junction, interface is weaker and metal 1 is able to glide easily on metal 2. So, what we require? We require weaker interface. If you want to avoid adhesive wear, we should go for the weaker junction, where the shearing between the metals take place at interface itself and is a mild wear. While in case of the stronger material, it will not have a weaker interface, or in the shear strength the interface will be more compared to even the soft metal, and that is why this kind of junk, this kind of a metal transfer occurs in this situation. So, this is important for us to consider the metal pair or situation which allow us only the mild wear or ultra mild wear. Now, let us take adhesive wear slightly on more detail. What we are saying that we need to quantify adhesive wear, and engineering we need to really come up with some sort of parameter, which parameter are more sensitive and how do we really adjust those parameters, how do we really optimize those parameters. So, what we say that to modeling the adhesive wear, we need to think about, maybe we need to take some assumption. Here we are taking assumption of the plastic deformation. That means all asperities which are coming in a contact, they are going to deform plastically, and real area of contact can be given represented by area A is equal to W is applied load, that is what we say applied load on the surfaces, and H is a hardness of weaker material or softer material. We will not consider hardness of hard material. Naturally, metal 1 and metal 2, one of the surface will be weaker or maybe lesser hardness. So, we will consider only the softer material or lesser hardness material. However, this assumption may not be 100% true, reason being the many asperities will go through the elastic deformation also. If suppose there are 1000 asperities between the metal and the interface, there is possibility is that maybe 900 undergo the elastic deformation and only 100 goes a plastic deformation. So, it will be kind of the hybridization, some plastic deformation, some elastic deformation. However, we can count this all using the counting the factor as something like a probability factor. That will come in the next few slides. One good thing about this is that how do we make a weaker interface. So, that is what in previous slide we say that we need to focus on a weaker interface. Weaker interface is possible if there is a surface film, that is what we say the surface engineering. If there is a surface film, then there is a possibility of lesser and lesser addition, lesser and lesser transfer of the electron. The electronic transmission will be lesser, metal transfer will be lesser, and adhesive wear will come down or maybe lesser in this situation. How it happens? Whenever there is a metal the metal is a finished or maybe the ready to be used as the product, there will be some sort of environmental pollution or maybe attack of an oxygen or fluoride or water on the surface. One way it is a good, reason being we are going to get a contaminated layer, and contaminated layer generally the layers are generally porous in nature, weaker in interface or weaker shear strength. And another good thing is that we will be losing only the material which is much lesser than 50%, and interface is lesser and material removal from a parent material is also lesser. So, it is a win-win situation. So, environment in a way, in a natural way, it is helping metals to reduce interface shear strength when they come in contact with other metals. So, that is an important aspect. The question comes, whatever we have understood, are we ready to model the adhesive wear, or do we need more knowledge related to adhesive wear for the modeling purpose? Now, if we require more knowledge, naturally we need to make some hypothesis. What is a hypothesis? You can say here, we say that two metals coming into contact, that is there is a metal 1, there is a metal 2, they come in a contact, and there is a asperitic contact, because metal needs to be supported on some mechanical support needs to be there. So, there will be asperitic contact. What will happen at the asperity? There is a possibility of the deformation of the contacting asperities, there may be plastic deformation, elastic deformation, and if there is a relative motion, that whatever the contaminated layer, that we say the protective oxide surface layer, it may get removed. Quite possible loose particles may be generated. The question comes, will this loose particle be useful or harmful? If the loose particles are soft in nature, then it may turn out to be like a solid lubricant. If they are hard in a nature, then it will lead to the abrasive wear, which we will be discussing in the next lecture. So, again we need to think about metal and a metal oxide or metal contaminated layer, what is the nature of that layer. So, we require that additional information. Another point comes, as I said, the stress level will be very high, there will be formation of the adhesive junction, cannot be avoided. If there is a surface coating, if there is a some sort of lubricant, then there is a possibility of lesser adhesive junction, or there will be junctions, but it can be easily shared, but formation of the adhesive junction will be there, and that is what has been shown in a B. But say the junction failure or junction growth, the first formation of the junction, and when the metal one moves in relatively to the metal 2, there is a possibility whatever this junction it need to be fractured or need to be broken. That is why we say the junction failure. And because of the junction failure, and then if it interface it is not really weaker, what will happen, the softer material, if I am assuming the metal 2 is a softer layer, will come, maybe say some sort of particle will get deposited or material will be transferred or particle will be transferred to the metal 1. That means metal 1 is going to carry metal 2 in form of this lump, or maybe say the projection system, right. And this has been already shown in previous slide how the metal transfer occurs. It happens because of the electronic transmission and then cold weld junction, and that is a reason why we need to think about this kind of hypothesis, or we need to generate this kind of hypothesis. If this process continue, what will happen? You are able to see there is some sort of material transfer, there is some material transfer. Even in a secondary coil, there is a possibility of some material in getting transferred from a metal 1 to 2. There is a possibility because of the work hardening, and then this surface is also getting some sort of deposits. And it moves continuously, maybe say for 10⁻³ cycles, 10⁻⁴ cycle, and there will be accumulation. You can see here that particle transfer and accumulation is continuously increasing, and here it is a complete big lump formation. Naturally, if the lump formation is bigger in a size and bigger than even asperities, this will also become under stress and it will get fractured from a surface. And you can see here this is a fractured surface or the particle which has been removed from a surface 1, and this is what we can say. Then the failure of junction by pulling out a large lump, bigger lump size, and then this is what we say that it is going to create a loose particle, and this is what we say adhesive wear may turn out to be abrasive wear. We will again study in detail about those, but not in today's lecture. We will be focusing only on adhesive wear in this lecture. Question comes, do we require more knowledge or we are ready to model the adhesive wear? In my view, before moving to the further knowledge or thinking about getting more and more knowledge, let us review what is our understanding about the adhesive wear. We understood that adhesive wear happens due to mechanical activity that gradually removes a discrete particle from a surface. If the metal to metal, naturally there will be interaction, metal will transfer first electron, and then complete material also will be getting transferred. Another point which we understood also, that microscopically even the smoothest surface will be rough at the micro scale, and then when the surfaces come in a contact, naturally what will happen, there will be only smaller contact areas which will be much lesser than apparent area. That is what we understood. And another one we mentioned about because the surface area or real area of contact is much lesser, there will be high local pressure, high local stresses, and under this high stresses what will happen, the surfaces will come into contact and make a cold junction. When they make a cold junction, that can be only avoided if there is some sort of coating or contaminated layer or some sort of lubricant. In absence of coating, in absence of contaminated layer, there will be a cold junction formation. When it happens in this manner, we need to break the junction if we want a relative motion between the two surfaces. There is a possibility one junction is broken, there will be chances of another junction formation, and if another junction is broken, there will be chances of formation of the third junction. So, this process will continue, and then continuous process will happen in this manner, unless if the metal selection or the material selection it has happened in manner which makes a weaker interface. If interface is stronger, adhesive wear will continue, and there will be a more and more material transfer from one surface to another surface. And finally, this transferred material will become a loose particle, loose wear particle, and then it will lead to the abrasive wear. So, this is important for us to review, and we are ready to now think about some sort of relation, and this relation was given long time back by Archard, but so we use the word Archard wear equation. I am emphasizing on a qualitative nature. This does not give a quantitative nature, reason being there are some assumption, and their assumption are also in the probabilistic in nature. We say one contact will fail, 2 contact will fail, 10 contacts will fail. So, it is completely probabilistic. In this manner, for time being, we say that it is a qualitative in nature. We need to understand what are the parameters which are involved in adhesive wear. For that purpose, we need to formulate the sum equation and then relate and come up with a final equation. What we started earlier, we say the real area of contact can be given by normal load applied on the surfaces and the hardness of the soft material. And then in this situation, we say also the two particles or the two surfaces when come in a contact, they are going to meet at n asperities. Number can be anything, number n can be 100, 1000, 10,000. We are just using the, because we need to formulate the equation, we need to assume some asperities. So, in this other situation or in the present case, we are assuming n as a number of asperities. Again, it may continuously vary because there are very high peaks, very low peaks, and there is a continuous possibility is that there will be variation. However, for time and instantaneous, we were assuming that there will be n asperities. Again, assumption is a plastic deformation. We already mentioned that plastic deformation is going to happen at the couple of asperities, but there is a possibility of elastic deformation at the other places. So, now if I think from a real area of contact which is in this manner A, will be what we will say, it is a summation of contact area at the asperities, and we know there are n asperities. So, we need to think about the summation, that means if there are n asperities, what will be the area of contact at asperity 1 plus what will be area of contact at asperity 2 plus what will be area of contact at asperity 3. So, this is what Archard equation, the formation starts with this. What Archard assumed, there is a some sort of a we say the semicircle or hemispherical asperities. When they come into contact, this is the one asperity which is approaching to another asperity, there will be some sort of overlap. This is the overlap has been shown, this is a perfect matching, again it will depart from this asperities. So, this is a process continuous happen, and we can say that as because in this case the radius is a, then area which will be maximum, this will be the pi a square, and if we multiply with the hardness, this will give the how much load will be carried by this asperity, or we say that each asperities, or maybe say if the area is a pi a square, will be carrying the delta W load. Similar way, we can think about the wear which is going to happen, loss of the volume from a surfaces. We can say that because this is a hemispherical, and assuming 100% asperity has been damaged or getting transferred from one metal to other metal, the area and then the volume can be given by 2 pi a cube by 3, and there is a some sort of a probability constant or multiplication constant. In this case, it can be some percentage, it is not 100%. So, we are going to give in this relation, and if I assume that the area and the distance travelled is the 2 a in this situation, because the overlap is 2 a in this is, it can be given that per unit sliding distance, that is a volume divided by per unit sliding distance, can be represented in this form, and the load is can be given present in this form. Now, we can integrate or we can sum up what will be the volume per unit sliding distance, what will be the overall weight which will be carried by the asperities. What is the important thing is that because we need to get rid of n which is unknown to us, we need to get rid of a which is also unknown to us. So, in this case we are able to find out what will be the total load in terms of pi a square and 1 to m. Similarly, we are able to find out pi A square by 3, which is related to the volume. And now, if I bring the volume in this manner and substitute by A square from this side, we will get an equation something like this. So, volume per unit sliding distance is a K2 divided by K1, W by H and 1 by 3. So, these are the important parameters. Let me say this is the applied load, this is the hardness, these are some constants, and then if we know that total sliding or is equivalent to L, we can find out overall volume which will be worn out from a surface, which can be given as a coefficient, that is a probability, proportional to W, proportional to sliding distance, inversely proportional to hardness. So, initially what we thought, if the area of contact we need to be increased, or if I say in a short that if I look at the first equation, A is equal to W by H. This indicates if you want to reduce a stress on the asperities, you need to maximize the area. If you want to maximize the area, you need to minimize the H. That gives us some interpretation. What we in this situation we say, if you want to reduce the volume of the wear, you need to maximize hardness. So, two different expression. In this expression we are saying we need to minimize hardness. In this case we are saying that we need to maximize our hardness. So, which one is correct? We need to understand this, we need to perform some experiment and come up with the right results. However, Archard says very clearly that wear volume is proportional to sliding distance, which is equivalent to L, wear volume is proportional to applied load, which is the W, wear volume will be inversely proportional to hardness of the software material, and the K1 is a dimensionless constant which expresses the probability of removing a wear particle. This constant may be referred as an index of severity. What is the meaning of that? We say when K1 is equal to 1, every junction involved in a mechanical interaction will be a wear fragment. It is 100% failure of the junction which are coming into contact. But K1 is equal to 0.1, that means only 10% or 1/10 of the friction junction produces wear fragments. If K1 is equal to 10 raised to minus 7, that means what? Only one failure out of the 10 million junctions. So, what we want minimum to minimum value of the K1. If we are able to design this kind of junction, that will be very useful for overall product design or from surface engineering point of view. So, this is our thinking that we need to think about minimizing the K1. But let us look at the nano scale, which we say that because macro scale everything was smooth, micro scale there was a rough surface, but what happens on the nano scale? Do we need to understand that? Yes, we need to understand it, reason being the local stress or relative motion related to the failure of junction, more and more easy pass or a weaker junction will allow better and better relative motion, lesser and lesser power loss. So, we need to think from that angle. Question comes, can we really measure adhesive force between the surfaces? Yes, it can be measured when we use atomic force microscopy. Similarly, we can infer what will be the real area of contact in actual area of contact. What Archard equation, it gives us some sort of a qualitative measure, but if you want a real quantification, then we need to use some sort of microscopy project or maybe say some profilometry, and we need to infer from that using the image analysis or using the image which has been taken from a very good source. So, these are the important aspects. Now, if I think from a wear point of view, we say there are some critical factors for adhesive wear, which is a surface roughness. We need to minimize the surface roughness is a one, but we also mention about we need to texture, we need to design a roughness if you want a better and better results. Another one is a chemical makeup, what will be the whether it is a metal or and it has with more surface energy, less surface energy, we need to choose from that angle. So, that is what the surface energy comes into picture, and last one is the operating condition. As you change operating condition, value of K1 will change. We will take one example in today's lecture where value of K will be changed. We will get a different value when we operate on the different RPM, maybe 30 RPM I will get a 1 K kind of K1, 60 RPM I will get another kind of K1. So, it will not be consistent, that means every K1 can be selected or designed as per the situation. Another point comes, as I mentioned, the nanoscale. We say understanding nanoscale adhesive wear is essential for developing new materials. If you are thinking about developing a new materials, naturally phenomena at a nanoscale is very important. Another, in surface engineering, we give a lot of emphasis on the coating. It can be soft coating, it can be hard coating, and it is important to minimize the wear and extend the lifespan of the machines. So, these are important aspects, and then what we say that as far as possible, try to minimize the surface energy. When the surfaces are generated or made, they will have a lot of energy. Good thing is that environment immediately react with those surface energy, and if there is a free electron, there will be some sort of oxidation, and we may get some sort of contamination layer. Fortunately, as I said, if I look at the iron oxide, and iron oxide are the 3 types of oxides. In some cases, it will be to 40% volume of iron and 60% will be other contamination. In some cases, it will be 42% or 48%. So, quantity of iron which is going in oxide formation is the overall lesser. First, it is a weaker surface. The oxide is going to make a weaker interface. So, weaker interface is essential, and in addition, material which is getting transferred or will be lost is also lesser. So, that is very important. If you are able to form the oxide layer on the surface, it will be very advantageous. Or if we can make the surface chemically inactive, that will be also important for us. We have this diagram to demonstrate how do we really perform experiment at a micro scale or nano scale. We see generally we have something like a pin, a cylindrical piece or a sphere, and then this is maybe a substrate which has some sort of oxide formation on surface. Now, if I bring this spherical ball in contact with the surface or cylindrical piece in contact with the surface and start rubbing or going ahead with the relative motion, it can be unidirectional, it can be reciprocating depending on the situation, or it can be the applied load, maybe say we are thinking about the fluctuating load, that is also possible. So, relative motion in this direction or in this horizontal or vertical direction, we can perform number of experiments. We know if we allow the clean surface, there will be electronic transmission. That means, there is a possibility if we have a very clean surface, few electron will get transmitted to this surface, few electron will get transferred to this surface. Typical is indium. Indium is a soft material. If I make a pin of indium and then use in a steel, the possibility is that steel will get some layer of the indium. Similarly, carbon material, if you bring carbon material in contact with some sort of steel, there will be layer transfer. So, transfer of the layer will occur. If this is what we are trying to show here, if we bring a steel ball in a contact, there will be some sort of rupture, and then there is a possibility of the removal of oxide layer, and there is also possibility of complete removal of oxide layer. There is a possibility in this situation. Same thing with the cylindrical piece, what we say in this case the pin comes in a contact, maybe initially there is no, and then the layer is getting transferred. In this case the layer is getting transferred. So, what are the points? We can do experiment with a pin, we can do experiment with a ball, and then there is also possibility that if we adjust relative speed, we can remove the transfer in this oxide layer completely or partly also. What happens in the situation, there will be some sort of asperity brokerage or the breakage, and then there will be debris which will be generated, and this debris can act in a good manner or bad manner depend on the hardness of the surfaces. That will be discussed in the next lecture on abrasive wear. We will be discussing these points. Now, let us look at what we studied about nanoscale. We say every metal when it comes in is formed, there is a possibility the bulk phase and the top surface is getting some sort of oxide layer, or maybe say the top surface is in high energy level, and then there is some sort of atmospheric gases which are going to act on the surface or react on the surface. They will be forming some sort of a contamination layer. This is very important for us. That means, if we do not get that kind of environment, we can generate that environment also. We can use some sort of fluid or maybe some sort of gases to make oxide layer, but it will be controlled. And we have known that there are some sort of additives which can form this kind of oxide layer on the surfaces. Now, if you look at from atomic point of view, atomic layer, we are able to see this color orange. There is a orange color layer. This is the front color, this is the black layer, and maybe side layer we are shown with a red color in this case. What we are saying, the electrons on the top surface can be high energy and the bottom one may be lower energy, and these high energy electrons will try to act with the other surfaces. So, let us take example. Now, if I say there is a sphere, then the surface 1, that is what surface 1 here, and then this surface is surface 2. Quite possible I make this sphere which is a much more reactive or maybe the softer in this situation, and then when we are bringing this sphere in contact with the clean surface, there is a possibility clean surface get transferred, or in this situation what we have shown, this is a transfer layer, a transfer of the atoms. So, this has been indicated that whenever there are two metals coming in contact, whichever is more reactive, it can really transfer electrons from that surface to the next surface or next metal. And this is important to understand and minimize or make a product which can really minimize the wear rate. Now, if I think from a much more detail, we can say that we can think about the severe wear, which is very essential to minimize. That means, if we need to choose a material which are in adhesive wear or which are subjected to adhesive wear, we should not think about a softer material. As far as possible, the material hardness of the two surfaces should be almost equal. If there is the softer material, what will happen? There is a formation of a transfer layer, and if that transfer layer goes weaker side, like it makes the interface weaker, it is very good. But if it does not make a weaker interface, and if this interface becomes stronger and compared to the metal 2 or metal 1, then that is a very harmful. That is what we have shown experiments, we have done some experiment on the balls or the 4-ball test. We have seen that there is a adhesive wear, and then if the load is very high, and then in absence of lubricant, we can get a lot of plastic deformation and almost a scissor kind of action, and there will be we say that the huge plastic deformation, cold junction, and then more and more you can see the more and more fragments are coming from a surface, that means the number of junction have been broken. So, this is what we call as a severe wear, which is important to consider. We want to avoid this kind of wear. What should we do? We say that whenever we use and we think about severe wear, one is a hardness, other one is can we change the phases. It's something like if compare iron with a steel. When iron has a lesser phases compared to steel, that means composition is different. In the situation, what will happen? Steel will not go for the high severe wear of or a severe adhesive wear, but iron can go. So, we must try to use a lesser and lesser pure metal as far as possible. Otherwise, we need to think about some sort of lubricant layer, because whenever we bring a lubricant layer, adhesive wear comes almost to 0. So, that is one. If you are not able to keep a lubricant, think about oxide layer, keeping some oxidizing agent there which can form the oxide layer, and that will also be important. So, there are number of measures, whichever measures are really useful, it will depend on the situation to situation. One situation maybe oxidation is important, other situation lubricants are important, third situation kind of hardness is important. So, we need to think from that angle. Now, just to elaborate all what we have studied, as I mentioned that Archard equation is kind of the qualitative nature, that it can really rank the materials, it can compare the materials. So, just to for that purpose I am just considering the one example. We see that let us find out the best material for dry journal bearing. Even though we know very well journal bearings are liquid lubricated or gas lubricated, but in this situation we are choosing a dry journal bearing and we want some material which by performing experiments on the pin on disc machine. Why do we require a experiment on pin on disc machine? Because the constant K1 which comes out for a material 1 may not be same under different condition. That means, whatever the constant A K1 for A may be different from one situation to other situation. So, we need to really perform experiments. Again, Archard equation gives a qualitative nature, not a quantitative nature, and we need to perform experiment. Archard equation gives some sort of parameter, which parameter need to be considered, which parameter need to be optimized using the experimental technique. We can go ahead with a much more detailed analysis, there is a possibility, but for quick results we can do direct results, we can get direct results from pin on disc machine in this situation. So, in this case again we have kept one disc material as the AI the SI1040 steel. That means the shaft material has been decided or the journal material has already been decided. What we need to do? Choose a bearing material. Bearing material can be A, can be B, can be C, can be D, can be E, and these are the some parameters given to us for material A. Where they have conducted the three condition. One is sliding speed of the disc is 30 rpm, load is 100 Newton and duration is in minutes 350, and they are getting some sort of wear scar of 9.7 mm. And then in another situation, so again in material A, RPM is same, but load has been doubled and the time duration has been reduced, while in this case the wear scar is 8.81. This does not mean that this material and this condition is better than this, it is just the results, and we need to put those all parameters into the Archard equation for the comparison purpose. Coming to third side, we say that now RPM has been doubled, load has been doubled, but duration has been reduced, but still we can see the wear scar has doubled. That means there is some sort of a thermal related problems, maybe the thermal dissipation is not happening quite fast in this case. Coming to the material B, they have conducted two tests, one is 30 rpm, one 60 rpm, load is remains same and then time remains same. We are able to see at a higher load it is giving the 15.27 SKR, maybe say and the high speed is gives a 15.27 mm as a SKR, and 30 rpm it gives a 12.63. Material C, material D and material E are also materials. And what is the observation in this case? What we say, minimum scar diameter is 8.81, maximum diameter is a 20.83. This doesn't mean that this material is a worst material. It is just a values given to us, and we need to use Archard equation for comparison purpose. And as I say, the wear scar, and this has been shown in this. This is a pin which we have used, or maybe particularly in this example we have picked up, and this is a wear scar. A maximum value of wear scar will be equivalent to 2R, it cannot be more than 2R. That is a one. And then once we know the wear scar value and the radius of the pin, we can find out what will be the wear volume. That is how we can drive this relation, and but it is well established. Another thing is that the different wear scar is happening because of the different condition, and quite possible we may get a different value of K1. It is important, and this is what has been shown, whatever we have shown in 3-dimensional model. In this case, it has been shown in a sketch in much better manner, and this is the depth of a scar. Sometime we can give this relation in terms of H. But this is a more appropriate or more common that you give a results in terms of the wear scar, which is easy to measure. So, this is a steel surface, or we can say the shaft surface or journal surface, and this is the bearing surface, and we need to choose a bearing material. So, whichever material related to pin is the best, we need to choose that material. So, this is also been shown, and then when we want to apply a normal load, we apply a normal load on a pin. First, we need to ensure that there is a contact. If there is no contact between two surfaces, then it will wear will turn out to be 0, it's no use. Another thing is that this has to be perfectly aligned. That means align the load line and axis of the pin has to be aligned completely. And third thing is that there should not be misalignment between the disc and the pin. So, this needs to be set properly for the good quantitative results, otherwise we will not be able to perform. And there are well known pin on disc tribometer available in almost every lab, or every institute has this kind of interface. You can see here there is a pin holder, there is a pin, and the load cell can be used. It can give a two direction load, is a vertical direction and horizontal direction. That means we can also measure the friction force in this situation, and this is the test disc. Whatever we have shown something like a text and the test disc in this case, so that we can figure out what will be wear track. There is a possibility even the disc may wear, but we try to keep a hard disc, a disc which will not subjected to wear, otherwise it will be costly to change the disc again and again. That is why we always keep a softer material, weaker material as a pin form, which is much easier, cheaper to change continuously. Well, not maybe from one experiment to another experiment, but not disc, because disc is a bigger one and more costlier, and then fitting and removing again is costlier. It will take some time to us. So, these are some setup and experiments were done on this kind of thing. And what now we can think about the Archard equation. Archard equation we have already derived in this form. We say K1 into normal load into a sliding distance inversely proportional to hard disk. And in previous slide we say the wear can be given in terms of pi d4, that is a wear the scar given, and then this is the radius of the pin. And the sliding distance L itself is given as a test duration in sliding speed. When we substitute, we can find out what will be the K value of K1. Here the D is known, H is known, R is known, L is known, and load is also known to us. And when we do a calculation, what we find, this is the material A, and then we get all three values, and this is the worst case 0.82. That means Archard equation, even something like we can think about the linear relation, but it is a highly non-linear. That means as a condition changes, value of the K1 is changing, it is not remaining same for the material. So, for material case 1 we find 0.075, for case 2 0.09, and for case 3 0.82, which is one of the worst. The worst case, that means third number should not be used at all. Now, what is the best material? Best material is a B, which is also giving some sort of consistency 0.021, 0.022, that is a statistical variation. So, we can say the material is the best material in the situation. Other materials, if we do not get a B, then we can think about the C, we can think about the E, and or maybe the D also. So, if we do not get a B, then we can think about E or D. So, this is the way that we can say that some sort of a quantification will come by performing experiments. So, is even that there is a equation given by the Archard that can be utilized under dry lubrication condition to figure out which material will be the best material under different conditions. Now, finally, we can say there are some sort of take home. We say the adhesive wear is a natural phenomenon, because when metal come into contact and they are subjected to mechanical force and relative motion, adhesive wear cannot be avoided. That is important aspect. What is the second take home? We say that metal to metal K will be always more compared to K non-metal and metal. That means we should choose and give more preference non-metal to metal. There is also possibility that we can give preference to non-metal also. However, as we say that we need to conduct a number of experiments to come up with the right results. Another point is that same material should not be used, because in case of the same material there will be more and more transmission of the electrons and more cold junction formation. Naturally, to shear those junction, it will take a more force and more, it will cause a more wear. So, metal A and B will be preferable compared to metal A and A. metal and then compared to metal contact, non-metal contact will be preferred, non-metal contact will be preferred. Another point is that if you want a longer service life, try to keep ultra mild regime. So, in my view, K should be something like maybe say lesser than even 10⁻⁻15. In previous slide, we say that even 0.02 was a good material, but we need to think about better material compared to these materials, right. Now, the last one is of course, as I mentioned that in this case we should choose a dissimilar materials, and then if we are not able to choose the dissimilar materials, think about a maximum hardness. We can maximize hardness, even though we mentioned about the real area of contact will increase with a lesser we say the hardness, but that is good only for the EHL case, what we use the word elastohydrometry lubrication case, but not an adhesive wear case. So, this is the important observation. Now, another point comes, if we are not able to prevent adhesive wear, what should we do? In this situation, routine maintenance is important. That means, whatever the wear debris getting generated immediately need to be cleaned, or maybe so once in a week or once in a month, depends on the situation. Though if those particles are continuously cleaned, then surfaces will be in a better form, area of contact will be more. Otherwise, if there are more and more debris generated and remain there, area of contact further will come down and it will cause a more and more wear rate. So, if we are not able to prevent adhesive wear, think about maintenance. Otherwise, mild wear will turn out to be the severe wear, reason being there will be fluctuation in load, maybe stress level will increase, because it is going to be subjected to only the particles are going to subjected to load and increase in stress, and sometimes speed will reduce or speed will increase, and there will be increase in a friction that will increase the temperature also, or a combination of all. So, what we say, adhesive wear as far as possible minimize, use weaker interface. Naturally, weaker interface can be made from A and B compared to AA, can be further weaker and can be made when we think about non-metal to metal, or if we have some contaminated layer, that will also make a weaker in this situation. So, if we are not able to do any of this, we choose a high hardness. If you are not able to do that also, think about the relative, think about the maintenance or routine maintenance, it can be weekly or monthly, depends on the situation. So, next lecture we will be focusing on abrasive wear and erosive wear. We say mechanism is the abrasion and erosion, and the wear caused by because of abrasion will be known as abrasive wear, wear caused by erosion will be named as a erosive wear. Thank you.